right, good afternoon, everyone. Welcome to class. So we'll have another lecture today. I think this will be our last lecture. And then whatever we cover, whatever I cover is what I cover. And then Monday we'll have a review. Okay, Monday's review from Wednesday's test. I understand Wednesday is research day. Speaking of research day and award ceremony, our own classmate Joshua, who sits in the back next to Adriana, actually they're lab partners. Well, Joshua won the Madame Curie Award for the best general chemistry student. So when you see him next week, he's not here. His grandfather passed away. But if you see him, just give him a congratulations. I think next Wednesday they will say his name or do something for Joshua. I'm not sure what, but it's good someone from our class got it. And I think someone else from Dr. Hooper's class. And I'm sorry, Elena, you didn't. I nominated both of them, but Stephanie chose hers, and I had to make that choice. And so, anyways, if there's a runner-up, I think the award is a chemistry set. So I think she's out of a chemistry set. So, anyways, excuse me. So today is March 31st, 2021. And so test next Wednesday. All right, should cover chapter 15 and 16. And we'll have a review on Monday. So make sure you come to class. Remember, this test was originally for Monday, but because of Easter, I didn't feel like giving a test after Easter Sunday. So quiz 3 is also due on next Wednesday. So upload that, and we will get that graded. So lab reports, please be up to date and up to speed on your lab reports. I think you guys should start turning in Le Chatelier's principle, so turn that in, and then we will grade it. Either myself or my work study student will grade those lab reports for you, and it will give you some points. Homework 16, let's see if we can knock those out and turn them into me on Monday for 10 points. Excuse me. I believe Monday's April 5th. And make sure you do your clutch prep online homework assessments. This is extra credit. And make sure you update your lab notebook. At the end of the term, I will collect your lab notebook. People are coming to lab, which is great. I appreciate you all coming to lab, definitely. But I'm not signing any lab notebooks, so make sure you turn in your lab notebook at the end of the term. Anything else you guys can think of? There is a lab that we're doing concurrently or currently, and that is the problem set. All right, so probably let's make that do, well, some of these problem sets will be on the exam, though we will have a review on Monday. Let's make that due next Friday. Okay, so for those of you that are a little bit lagging behind on this extensive problem set, make sure you do that, work together, and check your answers with my answers, see if they match. Right, that is your lab, actually. A whole lot of titration problems. So let's go ahead with today's lecture. Once again, this will be the final lecture before we take test 3. And I want to go over a problem involving Q. Okay, Q. Okay, so here we're going to put Q first, and we will compare it to Ksp. Okay, the equilibrium constant that we're talking about is Ksp here. And we're asking ourselves the question, will a precipitate form or not? Will a precipitate form or not? So we want to put Q first. If Q is greater than KSP, the alligator jaws are pointing this way. It's pointing towards the solid, and that would mean you would get a precipitate or a formation of a solid. If Q is less than KSP, remember, put Q first. Put Q first. Here the alligator jaws are pointing to the right, and that means it will not precipitate. You'll just have the ions dissolved in water, so it will just remain in solution. And then finally, if they are equal to one another, if Q is equal to KSP, we're kind of at the edge. Okay, we're kind of at the edge here. We're not a precipitate, nor are we a solution. We call that I think, supersaturated solution or saturated solution. Okay, so this is called alligator rule or gator rule. For this to work, you must please put Q first. Okay? Q first. Let's do this problem here. I think there's a problem like this on Wednesday's exam, multiple choice and I think problem set. So example 4 is what we'll do now. If 2 milliliters of 0.2 moles per liter NaOH are added to 1 liter, that's a lot, of 0.1 molar calcium chloride, will we get a precipitate? Okay, will we get a formation of a precipitate? Solid. So first off, I'll just go over this with you. You see the solution here, but let me go over it. First and foremost, you have to realize what is the identity of the precipitate. So 2 mils of 0.2 molar sodium hydroxide. Remember, in water, this is nothing more than sodium ion and hydroxide ion. And here in water is nothing more than calcium ion and chloride ion in water. I don't know if you remember this. There's something called the solubility table from General Chemistry 1. And it turns out if you look at your solubility table, the calcium ion, pluses go with minuses, right? The calcium ion and the hydroxide ion actually do not go into solution. It precipitates out. It's a sparingly soluble solid, and sparingly soluble solids have a Ksp. So this is the equation that we're really concerning ourselves with, and it's this. Calcium hydroxide solid. Okay, so here you need to recognize it's calcium hydroxide that will form the solid. I'll tell you that on the exam, or have a solubility table handy with you on the exam. This is from Chem 1. Okay, sodium is usually what's called a spectator ion. Chloride, Cl minus chloride, is also called a spectator ion. They just remain dissolved in water. Really, that's all they are. They just remain dissolved in water. But this is the real equation that we want to concern ourselves with. Okay. This has a Ksp, and the Ksp is given to us here as 8 times 10 to the minus 6. Okay, it's a pretty small number. 8 times 10 to the minus 6. And remember here, at an equilibrium, back and forth, for Ksp, I want you guys to use S. Wait a second. What do I need to do here? Okay, balance it is what I need to do. Okay, there. Good. Balance the equation. Almost made a mistake. Okay, if this was an exam. All right, now for the ice table, this will be plus S, and this will be plus 2S. This will be plus S, and this will be plus 2S. All right, let's go back here. Let's take a little bit, let's go back to the problem. That's at the heart of the matter. We have here sodium hydroxide, and let's figure out the final concentration of OH minus. We have 2 milliliters. Let's go ahead and convert that to liters. 1,000 milliliters is 1 liter. So 0.002 liters. Okay. So we have here 0.002 liters. That's our volume. The concentration on the bottle, are you guys following me here? 0.22 big M. We're going to divide this by, what's the total volume? 1 liter plus 0.002 liters, it's going to be 1.002 liters. That's the total volume. Here, the liters cancel out with one another. And doing this on my calculator, you may want to check my work here. 0.002 times 0.2 divided by 1.002, I'm getting 0.0004. Okay, big M. That's our final concentration of OH minus. Let's figure out the concentration of calcium ion. Calcium ion is going to be 1 liter times 0.100 molar. Total volume after we mix all of the calcium ion and the hydroxide ion, the total volume is going to be 1.002 liters. The L's and L's cancel. And doing this on my calculator, I'm getting 0.0998 big M. So this is our total volume. This is our final concentration. Okay. Let's go back here. I want to direct your attention to right here now. Let's complete this. So the Ksp here is going to equal to concentration of calcium ion times concentration of OH minus. What should we do? Raise it to what power? 2. Okay. All right, so this is plus S at equilibrium. This is 2S. What do we need to do with that 2S? Square it, okay? Okay, the calcium ion concentration, which is S. By the way, S stands for solubility. So for Ksp, use S. You can use any letter, really, but your textbook and others use S. Because we're really asking ourselves the question, out of this solid, how much of this goes to calcium ion and hydroxide ion? So plus S. Here we have 0.0998 for calcium ion. Hydroxide ion is going to be 2 times, you guys following me here, 0.0004. 0.004. Okay, we got to square that whole thing. We're going to ask ourselves the question, does this equal to Ksp? Okay, if it equals to Ksp, we have what is known as a saturated solution. Right now, this is called Q. So let's do this on our calculator. Okay, you got to be tricky here. There's a lot of potential to make calculator mistakes, especially when you are in a hurry for the exam. Okay. And then you have to square it times 0.0998. So 6.38 times 10 to the minus 8. Okay, the Ksp given to us in this problem is, let's go all the way back up here, the Ksp given to us in this problem is 8 times 10 to the minus 6. So obviously we are not at any type of equilibrium, so they do not equal to one another. So put Q first. Okay, this is what I would recommend. All right, so here's the Q that we calculate. 6.38 times 10 to the minus 8. The Ksp that's given to us in this problem, we look this up. 8 times 10 to the minus 6. Which is larger? Isn't minus 6 larger? Right? Yeah. Okay. Sometimes I'm dyslexic, things get back and forth. Yes, 8 times 10 to the minus 6, Elena made my mind straight. 8 times 10 to the minus 6 is greater than 6.38 times 10 to the minus 8. Which way do the alligator jaws point? Left or right? They're going to the right. So to the right means, come on. Thank you. To the right means, will this precipitate or not precipitate? No precipitate. Yes. Okay, so this will not precipitate at these concentrations and at these volumes that you add. So the answer, unfortunately or fortunately, is there is no precipitate. All right, so I believe there's a problem like this on Wednesday's exam, and I think we'll go over another one of these during our review on Monday. All right, so just make sure you are comfortable with these types of problems. All right. In fact, I think I have here in my notes that we'll do one more of these types, of this type. So here's an entire list of KSPs. Okay, I know you can see these so perfectly and they're so nice and clear, but the idea is that these KSPs are something we look up, and again, they're always capital K is always quoted at a specific temperature. Okay. So let's pick on one. Let's do one more example here. Let's look at silver carbonate. Okay, silver carbonate. We'll do one more of these ice table-like problems. So silver carbonate actually is Ag2CO3 solid. Okay, these are all sparingly soluble solids. And that is at an equilibrium with Ag plus and CO3 minus 2. Okay, aqueous. So again, all of these are what we will designate as sparingly soluble solids. These are not 100% solids. If they were 100% solids, there would be no need to write this back and forth arrow. And so the Ksp designates to what extent this goes in this direction. So let's do our ice table. Before we do that, okay, this is something that is tricky, but you have to balance it. Okay, balance it. So on an exam, write the Ksp equation for silver carbonate. You'll have to write something like this. Write the Ksp equation for calcium hydroxide. Okay, on the exam or written exam, you'll have to write something like this. And make sure it's balanced. All right, do our ice table plus not 1s, but 2s. And here it's just plus s. Okay, Okay, the Ksp will be given to us. I looked it up in this table, and it's 8.1 times 10 to the minus 12. Okay, so this is checking out the solubility. S stands for solubility. All right, our Ksp here is going to be concentration of Ag plus raised to what power? Okay, this is something students, based on my experience, kind of forget, miss. Raised to what power? Square, so don't forget this on any exam. Times CO3 minus 2 raised to what power? 1. Right, everyone see that? Two S goes here, S goes here. So 2S, don't forget to square it, S. All right, this whole thing, 2S squared is 4S squared, 4S squared times another S. So this whole thing comes out to 4S cubed. 4S cubed, solving for the solubility S, must equal to 8.1 times 10 to the minus 12. That's the Ksp given to us in this problem from this table. So now our job is to solve for S, solubility S. Okay, so it's going to be 8.1 times 10 to the minus 12 divided by 4 equals S cubed. Okay, so to get S, we will take the cube root. Okay, the cube root, which is 8.1 times 10 to the minus 12 divided by 4. And we'll take the cube root. To me, you have a cube root button in your calculator, but you can also do this, raise it to the power of 1/3. Okay, those are the same thing. So let's do this on our calculator. 8.1 times 10 to the minus 12, such a small number. Such a very, very small number. So really it's all in here. Really it's all going in here. Divided by 4. And I'm going to raise that. Making me look bad here. Where's the where's the raised to sign? Is it this guy? Answer raised to the power of 1/3. And 1.27 times 10 to the minus 4, big M. Okay, that's the solubility. So the solubility of Ag plus, the solubility of carbonate, how much of this goes into liquid, how much of this gets dissolved in water. And solubility of Ag plus is not S, but 2S. So it's going to be 2 times this, 1.27 times 10 to the minus 4, which is, what is that, 3.54 times 10 to the 2.54 times 10 to the minus 4. Okay, don't forget big M. And then the solubility of carbonate is just plain old S. At equilibrium, this will be 2S. At equilibrium, this will be S. We already calculated S here. So here it's going to be 1.27 times 10 to the minus 4, big M. So this is how much is dissolved in water. Goes back and goes in this direction. Dissolved in water. Deionized water. Okay, good water. So this is the pipeline on how to solve these types of equations, right, where we figure out how much of the concentration is here. Okay. And remember, what is big M before we leave this? Molarity, which is moles per liter. So in 1 liter of water, you'll have this many moles of Ag+. In 1 liter of water, you'll have this many moles of CO3 minus 2. That's what this is saying when you have this silver carbonate solid. Okay. I feel like I'm a little bit behind, but let's see. All right, let's do some practice problems here. The solubility of calcium sulfate is found to be 6.67 grams per liter. Calculate the Ksp for this reaction. So here's how we'll do that. 0.67 grams per liter. Let's convert that to moles per liter. And recognize calcium sulfate is this formula. All right, so 0.67 grams per liter of calcium sulfate. We realize that for every 1 mole of calcium sulfate, there's 136.01 grams of calcium sulfate. Okay, that's from the periodic table. And this is equal to grams cancel. This is equal to 0.00493 moles per liter. Moles per liter is nothing more than big M. All right, so this is plus S. This is plus S. So the Ksp here is going to be the concentration of calcium ion times the concentration of sulfate ion. They're both in a 1-to-1 ratio, if you guys can see that. So this is going to be S, and this is going to be S. So the Ksp is going to be S squared, solubility squared. Well, they already gave us the solubility here. And so we just converted it to moles per liter. And that's what we will do here, 0.00493 squared. And that will be our Ksp. And that's about 2.43 times 10 to the minus 5. Remember, these are unitless. K is unitless. Right, so that's how you go about solving this problem. Let's just skip example 6 here and let's move on to example 7. Actually, the answer is in page. The answer is in. So disorganized today. The answer to this, the worked out solution, is on page 10 on your notes. Okay. Worked out answer on page 10. Let's go ahead and solve this one, and then I think we have one more problem, and we'll call it a day. And we'll call it a chapter. Right, well, a precipitate form of exactly 200 milliliters of 0.004 molar barium chloride is added to exactly 600 milliliters of 0.0080 potassium sulfate. Okay, there is some information that I have to tell you here. And what I need to tell you is the Ksp of barium sulfate. Okay, this I'll give you on the exam. So the Ksp of barium sulfate is equal to 1.1, very small number, 1.1 times 10 to the minus 30. Okay, so that constant for barium sulfate is something I'll give you on the exam. Okay, so don't memorize that. All right, so let's first figure out the concentration of barium after mixing these two. So the concentration of barium plus 2, remember barium chloride in water is barium ion and chloride ion. And potassium sulfate in water dissociates to potassium ion K plus and sulfate ion SO4 minus 2. Remember, these are from your flashcards. SO4 minus 2, if you had me for Chem 1. If SO4 minus 2 is sulfate. So the concentration of barium ion is going to be 200 ml times 0.0040 m divided by 200 plus 600 is 800 ml. And then the mils cancel, leaving us with big M, moles per liter. And doing this on my calculator, I'm getting 0.0010 big M. Let's do sulfate ion. Here we have 600 mLs. The concentration is 0.0080 big M, moles over liter is big M. Total volume is 800 mils. Mils cancel each other out, and we are left with 0.0060 big M. Right, let's write our equation. Okay, make sure you write our equation. And the equation is this: BaSO4 solid is in an equilibrium with barium ion plus 2 plus sulfate ion minus 2. This looks to be balanced. Okay, it's charge balanced as well. So this will be plus S and then plus S. Right, barium ion, so by the way, Ksp here is concentration of barium ion times the concentration of sulfate ion. So it's plus S plus S. We already figured out S here for barium ion is 0.0010. This is big M, molarity. Concentration of sulfate ion is 0.0060 molarity. Okay, but K has no units, so we don't care about the molarity. So 0.0010 times 0.0060 is 6.0 times 10 to the minus 6. Well, the Ksp here is 1.1 times 10 to the minus 30. Under these concentrations, it should equal at equilibrium to your Ksp under these concentrations, but it does not. So always put Q first. You see, I put the concentrations in here for S, and then I put the concentration in here for sulfate. So I'll put Q first. Q is 6 times 10 to the minus 6. Ksp is given to us 1.1 times 10 to the minus 30. And Q is much, much greater than K. So which way will the reaction move? Where do the alligator jaws point? To the, yes, to the left, correct? So are we going to make a solid? To the left, yes. So we expect a precipitate. Okay, a resounding yes. Okay. When you mix barium chloride at this concentration and this volume with potassium sulfate at this concentration and at this volume, mix them together, you will precipitate out barium sulfate. Yes. All right, last here. Let's see if we can do 2 more problems in the last 15 minutes or so. Okay. And that'll be enough coverage for our exam. All right, so calculate the solubility in molarity, big M of AgBr in pure water, but let's do it here in 0.00100 big M sodium bromide. Okay, so part B illustrates what's known as the common ion effect. So part B illustrates the common ion effect. And let's do that right now. First of all, let me tell you what the Ksp of silver bromide is. That's something you'll get on the exam. It is a very small number, 7.7 times 10 to the minus 13. Okay, very, very small number. Again, that's something you'll be given on the test. All right, so what are we asked to find? We're asked to calculate the solubility. Okay, we're not asked, will it precipitate? No. Okay, how much of this silver bromide, how much of it, what is the concentration in terms of Ag plus dissolved in water and Br minus dissolved in water? Let's go ahead and write our equation. Silver bromide solid is at an equilibrium with Ag plus and Br minus. All right, so let's do our very short ice table. This is going to be plus S. Plus S, remember this is balanced, and plus 1 minus 1 is 0 on the right, and we have a 0 on the left. So plus S plus S. Okay, Ksp is going to equal to the concentration of Ag plus times the concentration of Br minus. Okay. Here the concentration of Ag plus is going to be S. Okay, but I would like to ask you this one thing. What would be the concentration of Br minus? It will be S, but what else will it also be? Remember, we're not having water here by itself, but what else do we have? We have sodium bromide, which is sodium ion plus Br ion. So what will be the concentration of Br minus? Not just S. You see there's 2 sources of Br minus. One is from this reaction going this way. Okay, that's one source. What's the second source? Right, the second source of N is NaBr. So this is actually S plus 0.00100. Okay? This is the common ion effect. Okay, here the common ion is Br minus. All right, so there's 2 sources of Br minus in solution in water. One is the reaction going, Ksp reaction going right, going to the right, shifting to the right, and then also from NaBr, which is nothing more than sodium ion and Br minus ion in water. All right, so let's do one thing here. Let's assume S is small. We can do that. Because, why can we do that? 7.7, you see, times 10 to the minus 13 is such a small number that very little of the Br minus is coming from the reaction going this way. Even though there's 2 sources of Br minus, 7.7 times 10 to the minus 13 is so small. Very small. And most of the Br minus that is dissolved in water is in the form of the common ion. So let's assume S is small. assume solubility S is small. And in that case, S plus 0.0010 is about equal to 0.0010. Okay, so the Br minus will be about 0.0010, 99% source of it coming from sodium bromide. Very, very small percent origin coming from the reaction going this way to the right because our Ksp magnitude is so small. So making this assumption makes our math easier. 7.7 times 10 to the minus 13 is equal to S times 0.00100. And we can solve for S here as 7.7 times 10 to the minus 13 divided by 0.00100. And on my calculator, I'm getting S to be, now here's where you want to put your units in, as 7.7 times 10 to the minus 10, big M, for moles over liter. Okay, so the answer here, the solubility of Ag plus. Okay, so here we're talking about solubility in 0.00100 NaBr. Not in water, but in 0.001 NaBr. The solubility of Ag plus is 7.7 times 10 to the minus 10. The solubility of Br minus is 7.7 times 10 to the minus 10 plus 0.00100, which is basically just the same thing as 0.00100 because it's so small. If you add it, you'll still get 0.00100. That's the thing. Right? 7 point is a good point. 7.7 times 10 to the minus 10 plus 0.00100 is still 0.00100. I don't want you to report
right, you'll be there all night.
all the digits in your calculator now. Okay. Yeah. Good point. Okay. All right, so that is the common ion effect. Okay, so if we do it the same thing, I know I skipped part A, but if you do it with part A, you won't have this, and then you just same thing. Okay, that's part A. Part B, you have to add this. All right, 8 minutes left, and let's see if we can do one last common ion effect problem, and that will do it for this chapter. Okay, yeah. All right, page 16 of our notes. Okay, that was page 15. And now we're on page 16. All right, last problem, and this is common ion effect. All right, calculate the solubility of silver chloride. Okay, here it's in grams per liter, but that's okay. In a 6.5 times 10 to the minus 3 molar silver nitrate solution. So, and then here we're having AgCl. Okay. So obviously it's not in water. It's in water that contains silver ion and nitrate ion. Remember, all nitrates are soluble. All nitrates are soluble. So this is really Ag plus and NO3 minus. Okay. Because all nitrates are soluble in water. And really in water, this is just Ag plus Cl minus. All right, another thing that I have to tell you here is the Ksp. and I'll give this to you on the exam. So the Ksp of AgCl, I looked it up, and it's 1.6 times 10 to the minus 10. Okay, very, very small number. I'll give you this on the test, the constant. All right, silver chloride is AgCl. And that is at an equilibrium with Ag plus Cl minus. So this is going to be plus S, okay? Is this really plus S? What's the concentration of Ag plus? You see, there's two sources of Ag plus here. Again, the common ion effect. There's two sources. Okay, what's one source of Ag plus? One source of Ag plus is the reaction shifting, the Ksp reaction shifting right. That will give you Ag plus. What is the second source of Ag plus? The second source of Ag plus comes from this 6.5 times 10 to the minus 3 molar. Okay, so the second source of Ag plus comes from the 0.0063 molar AgNO3. So this really isn't S, which is coming from the reaction going this way, but there's also the common ion, which is 0.0063. 6.5, thank you. Okay. Again, that's the common ion here. Yeah, that's the common ion. All right, so here there's the Ksp is equal to Ag plus times Cl minus. All right, so here Ag plus is not S. If I told you in pure water, yes, it's S, but this is not pure water. It's water that contains silver ion and nitrate ion. And so it's S plus 0.0065 times Cl minus is S. And that has to equal to our Ksp, which is 1.6 times 10 to the minus 10. Okay, let's make an assumption. 10 to the minus 10, if you look at our Ksp, you see that's a very, very small number. It's a very, very small number, so we'll assume that our S is small. Solubility S is small. Very little of it goes this way as your primary source of Ag+, that's soluble. So when you assume S is small, S plus 0.0065 is approximately equal to 0.0065. So that makes our math a little bit easier. 1.6 times 10 to the minus 10 is equal to 0.0065 times S. So S solubility is 1.6 times 10 to the minus 10 divided by 0.0065. And here the solubility is something that you want to put your units in. I'm getting the solubility to be 2.4 times 10 to the minus 8 big M. So what is our solubility of chloride ion? Our solubility of chloride ion, how much of that goes back to get chloride ion dissolved in water, is 2.4 times 10 to the minus 8. And the solubility of Ag plus is equal to 2.4 times 10 to the minus 8 plus this 0.0065, and that's going to be about 0.0065. About, okay, because of the common ion. And all right, if you want it in grams per liter, okay, Yeah, on the exam, I do not think I'll ask you this, but if you want it in grams per liter, this is how you'll do that. You'll do 2.4 times 10 to the minus 8 moles over liter. Okay, these are the S you calculated. Times 1 mole of AgCl has 143.23 or 32 143.32 grams of AgCl. So in grams per liter, it's going to be about 3.50 times 10 to the minus 6 grams over liter. Usually, at least for my exam, you'll just end here. But if you take other chemistry classes, they may ask you to go a step further. How much of it is in grams over liter instead of moles over liter? Once again, on my test, you'll only stop at here. Okay, but okay, if you're asked for grams over liter, just multiply it by the molecular weight. Okay, you get it from the periodic table. The moles cancel. All right, it's exactly 1:50, so I'll see you all on Monday. Have a safe Easter and good Friday, I should say. And Monday is a review, so come with your questions as we do our review.